Hey, it's working. All right, cool.
Oh my gosh.
Yeah, all right, cool. Although, are you guys seeing any video? Oh, there we go.
Hello.
Let me see. Limbo and Peter, I still can't see you.
We can't see you either.
You can't see me?
Nope.
Okay. Jordan and Coleman and Henry, I can see you. Can you see me?
I can see you.
Yes.
Yeah. Is Gorbachev Kaylee or
It's Jasmine.
is okay, Jasmine? And I can't.
And my camera isn't working. It wasn't working for Greek either. So
She must be.
Okay.
yeah.
All right. Kira's on. All right, cool. Down to the wire. There we go. Bad timing. Okay. I'm going to go ahead and get started just because we have very limited time at this point. I sent out the guidelines for the presentations. You guys have most of you sent in your responses, and it actually looks like I have useful information this time. So I'll be able to send you some emails over the weekend to ask if you'd be interested in being in a group together. There's people who said they really want to work with students elsewhere, people who said they really want to work with students in their home school, and I think it'll work out to being a good balance. And there's good overlap and interest in topics, so I think we're going to be fine there. I also provided you with the rubric that I'll use to grade it. Take a look at it. You'll notice that like a quarter of the credit will come from simply meeting some basic checkpoints that are really going to help you get it done in the first place. A quarter of the points comes from it looking okay. A quarter of the points come from your delivery, and then only one quarter of the points is actually about the physics itself. My main thrust is I want you to get the sense of what will make a good what really matters in giving a presentation to a group of people is having them able to listen to you for that time. Hey, sorry, 1 second. Jen? See if I can get my kids quiet. Oh boy. Okay. On to today's topic. I shifted some stuff around. I'm going to do superconductivity today because I thought it would be the most fun for us. And nice.
This is what happened in Colombia. Exactly what happened. Well, maybe it's your phone. Yeah, it's data.
We can hear you guys. Limbo and Peter. All right. Window. Okay. All right. Awesome. Why is that? Window. Come on. Okay. Can you guys see a picture of a guy with a mustache?
We could a second ago, but it's gone now.
Yeah, it's fine.
Gone? Let me try again. Why is it?
We can see it now.
Yeah.
Is it all like garbled looking though?
Yeah.
Yeah, it looks like that here too.
Down the
Yeah. All right. Hold on. I don't know what's going on with that. It's just not a good technology day.
All right, I think we are okay now. Yeah.
Yeah. Okay, there we go. Does that look okay for you guys now?
Yeah.
All right, cool. All right, so
see it.
today's topic is going to be. You don't see it anymore? Why is it?
I don't know.
Yeah,
We
Oh, that's weird.
we can't see it.
Now you see it again?
Yes.
Oh, yeah.
Okay.
There we go.
It's being funny. I have to have like the program highlighted. It's cool. All right. We're going to talk about superconductors. Now, the guy on the right is a guy by the name of Kamerlingh Onnes. And the story I've always been told about him and his discovery is really pretty a funny one. In 1911, something very important was done for the first time. At that point, the coldest things that we have made were liquid nitrogen temperature on the order of 90 Kelvin, something like that. But in 1911, we managed to make liquid helium, which has a temperature on the order of 4 Kelvin. Now, Kamerlingh apparently, according to what I've been told by my professors, was kind of a jerk and really liked just publishing whatever he could. And at the time, people were just measuring the resistivity of materials as a function of temperature, and nobody had cooled anything down to liquid helium temperature yet. So he was like, I know what I can do for a paper. I'll just measure resistance as a function of temperature, and with the temperature going down rather than up, and we'll see what happens. And so he got a bunch of his grad students to start doing this project. And I think he started with mercury. He froze mercury, and then he started cooling it down to liquid helium temperatures. And his grad students, I want to make sure I don't. His grad students started measuring the resistance as a function of temperature as we go downward. And the resistance was dropping roughly linearly. And it got to one point, and it simply went away entirely. The resistance went to literally zero, almost exactly at the liquid helium temperature. And so he told his grad students that they were idiots, and he fired them. And then he got a bunch more grad students to do the same project. And they took the resistance as a function of temperature, and it came down, and then it dropped off, and it just looked like the equipment was breaking. And so he just kept firing grad students. And slowly over time, he began to feel that, well, maybe this wasn't the grad students' fault. And he published his data along with the sad grad students who made it. That's my sad grad student face. And there it is in the middle there. The resistance actually went to an immeasurably small number. And he published his findings finally, accepting that it seemed to be real, and eventually won the Nobel Prize for finding what was superconductivity. But there was no explanation for why a very normal behaving resistance would go down with temperature and then suddenly precipitously decline to actually nothing, to no measurable value whatsoever. So some people started working on an explanation. These are the three guys who eventually were credited with it. I would assume that these guys don't look familiar to anybody, but the guy on the left, that is John Bardeen. He's an American physicist, and he has 2 Nobel Prizes. One for developing the theory of how superconduction worked, and 2, a modest accomplishment, inventing the transistor. I'm not sure how much you're aware, but transistors are everything you do all the time, right? A computer chip is made out of billions of transistors linked to one another. They're logic circuits that allow you to turn switches on and off, sending data ones and zeros. And so every computer in the world, every iPhone and Android device, every tablet, every smart television, every Xbox, everything that you play with on a daily basis is because of this person right here and the invention of the transistor. It is probably the most important accomplishment in the history of technology. And then he also explained superconductors. So he's not bad, is what I'm saying. The guy on the right is a guy named Schrieffer. I don't know much about him. Nobody talks about him as much. The guy in the middle is Leon Cooper. He was the young guy in this group at the time, and he's actually currently a professor at Brown. I don't know if anybody's going to Brown, but if you go to Brown, try and meet Leon Cooper. He has a Nobel Prize for helping to explain super.
Kayla is.
I'm going to Brown.
You are?
Yep.
Well, go find Leon Cooper. I mean, Nobel laureates tend to. Who did I meet? I met Eric Cornell, the guy who developed the first Bose-Einstein condensate experimentally, and he bounced from university to university just saying like, hey, pay me $20,000 more, and the university would be like, okay, and he would just move from university to university making more and more money, and then they get where they want to stay, and then they're like, I want to teach one class. I want to do the physics of electric guitar, and that's all I'm going to do. And they're like, that's fine. Can we just put your name on this piece of paper? Yes. Leon Cooper, he teaches like, I think it is physics of music or something like that. But he teaches a class that he finds fun, or maybe it's actually really basic intro physics. He just does whatever he wants because he's Leon Cooper. But apparently he's a very nice guy. All right. So these three guys came up with an explanation for superconductivity, and here is essentially how it works. There are many classifications of particles in the world. One of the big dichotomies in particle physics is bosonic particles versus fermionic particles. Bosonic particles are objects that do not have to obey the Pauli exclusion principle. They can exist, as is suggested in this drawing here. They can exist in the same quantum state as other bosons. An example of a boson is a photon. Two photons of light can be in exactly the same state. Photons don't repel one another. Fermionic particles are the ones that we have mostly been talking about lately, things like electrons. They cannot exist in the same quantum state. They do have to obey the Pauli exclusion principle. They exert forces on one another. An interesting facet of this whole thing with the Pauli exclusion principle is that it's actually a force. It's just the electrostatic repulsion. When you get two electrons nearby one another, they exchange photons, push on each other, and shove each other out of the way. Bosons don't exert these forces on one another in the same way, and so they don't have to obey the Pauli exclusion principle. So these have to be in different states. Okay. Now, if you study quantum mechanics more, what you'll find also is the way you identify bosons versus fermions. These things have what are called whole integer spin quantum numbers. We haven't done spin quantum numbers. Spin has to do with angular momentum in the way that you would kind of classically think, although it's a little bit weirder. One way to think about spin is a measurement of symmetry. An object with a spin of 1 is an object that you could, if I had it, let me see here, like an arrow would have a spin of 1. If I rotate it around 360 degrees, if I spin it once, it returns to its original state. An object with a spin of 2 would mean that when you rotate it once, it goes through two symmetry points. A double-headed arrow has a spin of 2. If I rotate it only 180 degrees, it returns to its original value. Okay? Something with a spin of 1/2 is very strange. It is an object, like, for example, an arrow that is itself spinning, that if you rotate it around once, it comes back inverted afterwards. And that's a very strange thing to think about. But if you take an electron and you force it to rotate 360 degrees, its spin will be inverted when it flips over. It has to do with its magnetic moment and the fact that you would actually need to rotate the electron twice, fully around, to get it back to where it was. Very strange to think about. An object of a spin of 0, and this is the important part. An object with a spin of 0 if you spin it, it goes through an infinite number of symmetry points. The classic example of a spin zero object is simply a sphere. No matter what distance you rotate it, it is back to its original state immediately. Every whole integer number, including the number 0, count as whole integer spin and identify objects as bosons. If you get nothing else from that last diatribe of information, it is this. Electrons are half integer spin. They are fermions. They can't be in the same state. Bosons, even ones with a spin of 0, can be in the same state. And anything with a whole integer spin can be in the same state. So, electrons, not same state. And they have a spin of plus or minus 1/2, meaning they have to be rotated 2 full turns for them to return to their original state. You knew that electrons had a spin of plus or minus 1/2 from chemistry class. I'm willing to bet. Okay. Now, if we look at the conduction, oops, I didn't want to go that far. If we look at the conduction band in a solid, I'll go back down to here. If we look at the electrons that are in the conduction band inside any solid, it's comprised of electrons, and they're filling up this density of states because they all have to obey the Pauli exclusion principle, because they're all half integer spin objects, and they cannot be in the same state. If electrons were bosonic, all of them would just could pile up down here in the ground state as long as it was cold enough. As things get hotter, they might jump around and fill up a few more states. But if you made them cold enough, if you made a bosonic particle cold enough, they'd all just fall down to the ground state. Electrons wouldn't do that. If you cool them all the way down, they're simply going to show up in that very sharp version of this function I told you about, because they still refuse to exist in the same state. The question that arose once quantum mechanics was a little better understood had to do with the fact that a possible explanation for superconduction essentially revolved around the fact that the ground state for a particle within a metal has no position dependence. The probability density and the energy changes not at all when you move the object from one location to another. So it takes 0 work to move objects from one location to another if they're in the ground state. So the thought was, what if electrons weren't fermions? If they were bosons, we could cool the object down just like Onus was doing. Then at some certain point, all of the electrons would fall into the ground state, and then suddenly it would take no work to move them through the object. But that doesn't make any sense because they're fermions. They obey the Pauli exclusion principle and they repel. And that's where the guy in the middle comes in, Leon Cooper. He had this idea. Electrons, as they move through the lattice, they're negatively charged, and these ions are positively charged. When they get nearby the atoms, they pull in on them. And as they move past, they send vibrations through the lattice. Those vibrations are called phonons. Now, where does that name come from? How does sound travel through the air?
Vibrations.
How do vibrations work? I just want to be able to see your faces here.
Varying pressure.
Waves, probably.
Okay. How does that happen? Like, how does the pressure vary in a gas?
Well, it's like how, like, as I'm speaking, I'm pushing air out at different, like, in different ways, and because I'm pushing it out in different ways, it creates a wave or vibration in the air.
You push the air out, and what literally happens as the air gets pushed out of your mouth? What happens to the air the molecules in the air?
They vibrate.
Look at, like, slow down time, and in your mind think about what is actually happening in order to make the pressure in air greater, what has to happen to the molecules?
Go faster in some places than others.
There's more of them in a certain volume.
Yeah, there's more of them in a certain volume. They get closer to one another, right? What happens when you get atoms closer to one another? What happens to them when you put two atoms, both surrounded by electron clouds, really close to each other?
They repel.
They repel. If you get them really close to each other, they might bond together. But as long as they're only like pretty close to each other, they repel one another. So when you speak, you push air molecules so that they're closer to others. They push on the air molecules in front of them, shoving them out of the way, which then that wave progresses through space. But what kind of force actually causes the repulsion of the atoms?
Electromagnetic.
Yeah, electrostatic. Now, it turns out in quantum mechanics that electric field isn't just a field. It is an exchange of photons. Like, every electric force is actually an exchange of particles. A photon is emitted and then collected. Inside our solid, if we vibrate the lattice, what's happening is atoms are getting closer to one another, ejecting photons at one another, and then that ripple is being sent through the lattice work. Because that exchange of photons results in a physical vibration in the solid, it is essentially a sound. And it is therefore a quantized sound wave. And so instead of a photon, which is a light quanta, it is a phone on. It is a sound quanta. These are quantized sound waves, which is just sort of neat to think about, and the etymology is cute. So let me go back to my my little diagram here. All right. So this lattice vibration gets sent through the solid, and this other electron here is heading through, and the wave that got sent through the lattice can then affect the path of this electron as it's moving through the solid. What Cooper said was that, strangely enough, what happens is that a spin-up electron moving through the lattice sends information, sends these phonons back to a spin-down electron, a +1/2 spin and a -1/2 spin object. If the lattice is hot, what's happening to all the atoms around here? If the lattice is warm at room temperature or something?
They're moving around.
They're moving around in what kind of way?
Vibrating?
Yeah,
In all ways, they're just kind of jostling around.
yeah, totally random motion. So as a consequence, there's this huge noise of phonons everywhere, all over the place, bouncing all over the place, making this completely chaotic. If we make the lattice work very, very cold, all of those thermal phonons kind of settle down. The lattice stops vibrating. And the only vibrations are the vibrations, the tiny little echoes being sent through the metal by the electron drifting through it. And what Leon Cooper said is that the one spin-up electron and the spin-down electron can become coupled to one another by an exchange of phonons. It's almost as if this electron like tells this electron like, dude, turn left, so it can dodge around the atom properly, so that they wind up having this joined dance through the solid, allowing them to essentially dodge the ion cores as they move through. That's kind of an artsy way of saying what happens. But what Cooper really said is, once they become coupled to one another, once the noise in the lattice goes away so that the electrons can talk to one another, they get stuck together, married to one another in Cooper pairs. I don't think he named them Cooper pairs. I think they were named Cooper pairs after he called them pairs. But they get coupled to one another. Oh, I'm sorry. I meant to draw this one as spin down. Sorry. So that they essentially behave as a single object. Now, we have a spin up electron and a spin down electron connected to one another. The phonon that binds them to one another is itself a bosonic particle. Photons and phonons are bosons. They don't have Pauli exclusion principle restrictions. What is the total spin of this object?
0?
It is in fact 0. We get a plus 1/2 and a minus 1/2. So that their total spin is in fact 0. And this is really strange, but collected together now, this Cooper pair is a boson. And so what happens is, going back to his data, there are thermal phonons traveling through the lattice, and they're getting quieter and quieter and quieter. So there's less and less lattice vibration, so that the electrons traveling through the lattice are experiencing less and less resistance. Then you get to this magical critical point where the noise is gone, and the phonons that exist solely come from electrons moving through the lattice. They connect all the spin up and spin down electrons to one another. They become bosons, and they fall down into the ground state. They fall down into the ground state where there is no position dependence. And any applied electric field whatsoever causes them to move with infinite current, with no resistance whatsoever. If you're feeling skeptical, scientists at one point took a ring of superconducting material that they kept in the superconducting state. They flashed it with a changing magnetic field to dump a current into it. Okay? Then they kept it at that temperature for 2 years. And then they came back with a Hall probe to measure the magnetic field it was generating, which would measure the current in the ring. There was no power source. There was nothing, there was no battery, there was nothing supplying voltage to keep the current going. The current hadn't changed in 2 years. There's no resistance at all. This is very, very weird. If you're feeling further skeptical, let me tell you about a different kind of thing that does this. Not that long ago, I think it was 2001, Eric Cornell was able to make a Bose-Einstein condensate. This is a fairly famous graph showing the distribution of atoms as a function of energy level. And I believe these were sodium atoms that he was dealing with, but he got atoms to condense down all to the ground state and coalesce together into a single lump of just stuff, of condensed matter all down at the same ground state level. And these were full-on atoms made of lots of bosonic particles. I'm sorry, fermionic particles. But their total combination made them whole integer spin objects that allowed them to fall down to these quantized, this ground state energy level. They would do all kinds of strange things. If you spun them, here's a picture of one. This is an actual picture of a Bose-Einstein condensate. Here's one kind of sitting still. You can actually see it with your eyes. Okay, I have seen them before myself. It's floating in a magnetic field in a vacuum chamber to hold it steady. What they then did is they took a I'm sorry about my kids. Hold on a second. Four-year-old twins. They are not cooperating. They would use the magnetic field to start spinning the cloud. And they try to spin it. Remember, this is an object you can see with your eyes. And it wouldn't spin until they got to the right spin value. Once they got up to a particular angular momentum, it would start spinning, and a little vortex would appear inside it. And then they try to spin it at higher frequencies, and it wouldn't work and wouldn't work until they got to an integer multiple of that original frequency. And as they kept spinning them at integer multiples of the frequencies, more and more and more quantized vortices appeared in it. we have lots of examples of taking fermionic particles and condensing them down to behave like bosons and exist in the ground state. And what's so unbelievable about it is when we do, we make macroscopic objects, objects that you can touch and feel, behave in entirely quantized ways, in quantum mechanical ways, like seeing a cloud of dust, really atoms, that can only spin at fixed frequencies right before your eyes, or seeing a piece of material where all of the electrons can fall into the ground state and therefore wind up with no resistance whatsoever. Okay. Yeah, let's see here. Okay. So up until about 35 years ago, I want to say, 70s-ish, we really needed to cool materials down to very cold temperatures, like liquid helium temperature, to get superconduction to occur. And then in the 70s, people found that these very strange things, these ceramics, made of layers of copper oxide, cuprate, with all kinds of weird other metals stuck in between, were reaching the superconducting state at temperatures that could be attained only with liquid nitrogen. And liquid nitrogen famously costs about as much per gallon as gasoline. So all of a sudden it became rather practical, or close to practical, to be able to cool these materials to a temperature to get them to the superconducting state to maybe use them for something. Because, I mean, wouldn't it be amazing? Something like 60% or 70% of all of the energy generated by our power plants is wasted to the resistance in the wires that bring the power to your house. If we had superconducting wires connecting power plants to our house, we would be energy independent for all of time. Like, there would be no need for fossil fuels or nuclear power or anything that anyone would ever be concerned with ever, if we could make a superconducting power grid. Keeping our entire power grid at liquid nitrogen temperature, we can't do. But obviously, it was a very exciting result to jump from needing to be at 10 Kelvin to being able to be at 130 Kelvin. That was enormous progress. We haven't, however, made much progress since then. Until about last year, we got some things that were a lot higher, although still not practical enough. The other thing that kind of sucks about these materials is they're ceramics. They're brittle, so it'd be hard to make wires out of them. It's also very strange that these things are superconducting, because all of the other superconductors before them were all metals. In fact, most metals on the periodic table are superconducting at the right temperature. It is very, very strange and not at all well understood. There's been breakthroughs in the past like 18 months on this, to be honest with you. Why these strange, very high resistance materials, these ceramics, suddenly become superconducting, and they're way better at it than metals. We just don't know. So that's all neat. But the thing that's really cool about superconductors is this diagram I have on the right. These arrows are meant to signify a magnetic field. And this blue thing is supposed to be a superconductor. If the thing is in a superconducting state, not in a superconducting state, that is, if its temperature is above the critical temperature, and we apply a magnetic field to it, the magnetic field can penetrate through the material. If we get it into the superconducting state, though, as soon as you apply a magnetic field, it, via Lenz's law and electromagnetic induction, can respond by generating any amount of current that you asked for. And as a consequence, it becomes what's called a perfect diamagnet. It exactly counteracts any magnetic field exerted on it, and in fact distorts the shape of the magnetic field, displacing them around it like this. Now, why is that cool? No pun intended. If you look, these field lines have now been made more dense here. When you make a field dense, like when electric field lines are close together in a diagram, what does that mean about the strength of the electric field?
Stronger.
It's stronger there.
And an electric field is actually a concentration of energy, right? So if I've made the field lines more dense, I've increased the energy. And physics doesn't like that. It wants the energy be in the lowest state possible. So if you were to have a magnet, if if what you had is like, here's the horseshoe magnet underneath this thing generating the magnetic field or whatever, and gravity is pulling down on this thing, the object, as it enters the superconducting state and the field lines are displaced around it, will float up in the air away from the magnet, increasing its gravitational potential energy to move farther away from the source of magnetic field, so that you're sort of in equilibrium. Like, here's the superconductor, you're in this place where the magnetic field has gotten a little bit weaker, so it's not as distorted, and it's in a better energy state. So a superconductor distorts magnetic fields around it to exclude them from its body, which can result in levitation. See? This is called the Meissner effect. Down here is a piece of, I'm going to say probably YBCO, yttrium barium copper oxide, one of these ceramic superconductors. And what you see up here is a floating magnet. Now, you may have seen videos on YouTube of frogs floating over strong magnets, like this is a magnet and this is a frog. You can make lots of things levitate over strong magnets. You apply a strong magnetic field, they behave as like OK diamagnets. You have to put tons of current in the magnet to make the field strong enough that the thing will float up. What's amazing about a superconductor is that you don't have to turn any power on. You just pour liquid nitrogen on this thing, and then eventually, once it hits the superconducting state, the magnet just floats up into the air. And when you see it happen, you are seeing something that is completely and entirely quantum mechanical in a way that you can touch with your hands. And it is a borderline religious experience for a physics enthusiast. And for that reason, at this moment, I now encourage you to go into your email. Go ahead and mute yourself if you haven't already, and watch the 2 videos I emailed you like an hour and a half ago, one after the other. The first one is cool because it shows a magnet. It'll eventually show a magnet like on top of the superconductor, and the superconductor gets brought from room temperature into superconduction, and the magnet floats up, and they play with it. The second one is the most ridiculous thing I think I've ever seen in my life. I'm going to watch them myself.
lines of flux need to go from the.
I could see your faces when you saw the moment it levitated. That was pretty awesome.
Join a leader in early childhood education.
Are you guys done with the videos?
Yeah.
Yeah.
Yep.
Yeah.
I don't know if you can see me laughing. Every time, I mean, the first time I saw the Meissner effect in person was 1998. And every time I see it, you can't. So what do you think was cooler, the track stuff or like when the magnet just kind of like is sitting there on the little disc and then it just kind of goes eek, for like no reason? I mean, you made it cold and it started to levitate. I don't know. What do you think?
I like the first part where it locked in.
Yeah.
What did he mean by locked? I didn't understand that.
Yeah, I don't. I'm not sure exactly. I think he was just kind of sort of making up terminology, but you can essentially think of, like, imagine the magnetic field coming out of the magnets around it, and once you place the object in a particular position, it will serve to simply hold that field in exactly the same pattern that it's in, and it doesn't matter what orientation you're in. It's actually like trapped, held into that field in its lowest energy state. And if you move it to somewhere else, you have to do work on it to change the shape of the field. But once you stop doing work on it, it'll just get locked, like here's that, in the position where you've changed the currents within the superconductor, you've changed the shape of the distorted magnetic field, and it'll simply maintain that afterwards.
How far is it?
Superconductors are superconductors. Good for them. They can conduct electricity with no resistance. That's great. We love it. But the Meissner effect is like the coolest thing that you can do. If you feel like it, I think a Yibco or a Bisco is a bismuth strontium copper oxide puck with a little magnet and tweezers and a little styrofoam cup to put it in. Is like $30 on Amazon. You can buy them. You just need to get some liquid nitrogen to cool them down enough to get them in the superconducting state. If you get one and you do it, know that when you're doing it, no one has any idea what's going on. BCS theory, the Bardeen-Cooper-Schrieffer pairing theory, doesn't work in these cuprate ceramics. We think that something similar to it is happening. But it is not well understood, although I do have to kind of put my hands up and say significant discoveries were made in the past year. We've also found people have been very upset that copper seems to be so special. All the materials we've made that do this high temperature superconductivity have been cuprates. And just recently, I think we got it to work in some silicates or something in the same column as copper. I can't remember which, but it was just in the news 8 months ago or something. I haven't looked closely at it. So the good news is that superconductivity is back on the table for something to be researched again. When I first started teaching this course, the government had basically stopped funding any research in superconductivity because we weren't making progress. We were unable to figure out what the heck was going on, and we were unable to really increase these critical temperatures much more than we did in the 80s. We made some decent strides. We have found some strange superconducting properties in buckyballs, in these giant copper spheres, although they aren't very good at it. They're not as good as these cuprate ceramics. Is there anything else I wanted to say about them? Oh, yeah. One really cool thing, these cuprate materials, these what are called type 2 superconductors, they have a couple of other strange properties. Let me go back to sharing real quick. So in a normal superconductor, where do I want to, here's my Meissner effect drawing. Here we go. In a normal superconductor, if we make, on the far right here, if you make the magnetic field strong enough, you eventually rip the Cooper pairs apart. And when you rip the Cooper pairs apart, the superconduction goes away. And the magnetic field can go through the magnet again. And so you can apply a really strong magnetic field, even though the temperature is low enough, and make the thing not a superconductor. I showed you this Bose-Einstein condensate thing for a second reason. When we apply strong magnetic fields to a type 2 superconductor, this is really weird. You can't take it out of the superconducting state. What happens is you create vortices of current, and the magnetic field pierces through the vortex, and the material around it remains superconducting. And as the field gets stronger, more and more vortices appear, and the magnetic field can pierce through, but the rest of the material remains superconducting around it. And the reason why, I have no idea. I have no idea how they work. So anyway, you might consider, as we go forward, looking more into superconduction as a topic, or you might think about these things, Bose-Einstein condensates, because they're super cool as well. I did not mean that joke in that way, because they're at nanokelvin, so they're cold. All right, I'll let that one go. Anyway, any questions about superconductors that I can attempt to answer for you?
Could you explain again how the levitating is helping conserve energy? I didn't really...
Yeah, if you move farther away from a magnet, the magnetic field is weaker there, right? Mm-hmm. And so as a consequence, you are not distorting the field as much. When the superconductor is in a place where the magnetic field is already dense, as those field lines are then displaced around it, it's a nonlinear increase in how dense the field eventually becomes around it. At a farther distance, you are making the field denser, but it's not that dense. The energy density isn't that high. So in the presence of if we weren't in a gravitational field, for example, you could put that magnet on top of the superconductor. I wonder if they've done this in space. I don't know if they've ever done this on a spacecraft, but it should be that you put the magnet on a superconductor, you pour the liquid nitrogen on it, and the magnet just shoots away with decreasing acceleration. It gets kind of quickly pushed away and then just moves until it wouldn't be interacting with the magnetic field at all. In the presence of a gravitational field, there's an equilibrium point. You're increasing gravitational potential energy while you're also decreasing that stored magnetic energy, and you reach some equilibrium where the field distortion is weak enough that any other increase in gravitational potential energy, the magnet would simply fall back down again. So basically boils down to an equilibrium between an increase in gravitational potential energy and an increase in the density of the magnetic field. I don't know if that's okay for you, but that's what I got. Anything else? All right, cool. Check your email over the weekend. I'll be emailing you individually to say, here are some groups I think might work out, and for you guys to pick a topic, and I'll say something about what you said in your surveys to kind of guide the conversation, and we'll go from there to figure out where we go next. Alrighty?
Can you tell us more about this? We were not here on Tuesday.
Yeah, take a look at the documents that are now in the Drive folder. But you are doing research presentations. You should look at the assignment sheet and see the layout of when the presentations are going to be and when the checkpoints are going to be. But you are going to be doing group or individual presentations on a topic in contemporary physics of your choice.
Okay.
Yep. But there's a fair amount of detail in Drive. And there's a somewhat updated version of the survey I sent you before that asks you questions about, whether or not it's important to you to be in a group. If you're in a group, is it important to you to work with somebody in a different school or in the same school? That kind of stuff. Alrighty?
Okay. Yeah.
Anything else, guys?
What about the things you taught on Tuesday? Did you see my email?
Yeah, we can talk outside of class about it. I don't want to hold everybody up for that. All right, okay. I will respond to you.
Thank you.
All right.
Okay.
All right, cool. I will talk to you guys later. See ya.
Thanks, Taylor. All right, bye.